So as this is a session on marine ecosystem and fisheries, I will start straight with some fisheries typical information. And what we can see here is the representation of the landings for the main fish species in the Barents Sea and Norwegian Sea combined for the last 50 years. So on the x-axis are the years from 1950 to almost today. And on the y-axis you can see the cumulated landings in 1,000 tons of fish. And different colors refer to different fish species, with some of the main ones highlighted: herring, caping, and cod. And what you can see from this kind of representation is that we have a system where different species contribute differently to the landings, but also their contributions vary with time. They have specific dynamics. There's some part of the fluctuation that look a bit like random fluctuations, but at the same time, when we look at this type of graphs, we have the impression that different things can happen, but not everything can happen. There are some patterns in these fluctuations. And you can see some patterns at year-to-year scale, but also some decadal patterns, like, for example, North Atlantic cod can vary in a relatively smooth way. But for herring and caping, you have long periods of near collapse and then huge abundance. Of course, these are catch data, so they reflect the activity of the fishery, which reflects the economic opportunities and so on. But they also reflect the state of the system, that is the abundance of fish in the ocean. Is the system resilient to external perturbations? And in the future, will it be resilient? And will we see in the next 50 years something that resembles what we see here for the past 50 years? So resilience is central to this presentation, but what is it? It's actually important to define terms before we start using it. And the difficulty with resilience is it has been often connected to, used instead of, linked with a number of other terms. And I here show some of these terms that are the most commonly found when you search for work on resilience, like vulnerability, variability, robustness, stability, diversity, resistance, adaptability, complexity, and probably a whole range of others which I haven't listed here. And sometimes this confusion between resilience and these other terms makes it difficult to compare the different studies, or even make it difficult for scientists to communicate about resilience. So I searched for definitions, and when I first prepared this presentation, on this slide I had 20 definitions, then later on I had 2, and finally I choose 1. And so just to say that this is not the only one, but I find that this is a very practical one, and it comes from the seminal paper of Holling in 1973 on the ecosystem resilience and stability. And Holling defines resilience as the ability to absorb disturbance and maintain function. Now, you may think that, okay, we had a problem which was to define resilience, and now we have 3 problems. Is to define the ability of what, to absorb what kind of disturbance, and to maintain what function. So we have to define 3 terms instead of 1 now. So I will go through these briefly. And the ability of what? Well, resilience, you can think of resilience for different levels of biological organization. Here I show it from individuals to ecosystems. In fact, you could go down to the cell level and go to the Earth system level, but if we restrain ourselves to biological levels of organization, so we can have resilience of individual, population, communities, ecosystem. So what would these different levels of biological organization be resilient to? So the kind of perturbations you can think of, and these are not exhaustive lists, but for individuals, we can think of resilience to a variability in food supply, fluctuations in the thermal environment, the occurrence of parasites and diseases. At the population level, perturbations can include fluctuations in recruitment, modification of habitats, and alteration of the demographic structure of these populations. At the community level, there can be loss or gain of species, modified phenologies or modified spatial distributions. And at the ecosystem level, there can be variations in the energy input to the system and alteration of the species interactions through top-down waste weight control. So now we've looked at for what kind of object we can define resilience, and to what this should be resilient, what kind of perturbations, but what function should they maintain. And this is often not very well defined. For individuals, the basic functions we can think of are survival, growth, and reproduction. For populations, the ultimate function that the population has to maintain is not becoming extinct. But for communities and ecosystems, it's actually very difficult to define what is the function that an ecosystem or a community should maintain in absolute terms. In relative terms, we can define it as a function of the goods and services that this ecosystem or community can provide to us. But from the ecosystem community perspective, it's difficult to define these functions. And what Holling did in his paper in 1973 is define this function mostly as the interactions between species. So what is trying to be maintained in the resilience definition is the interaction between species. And here, as I'm talking about resilience in the Barents ecosystem, I will focus on the ecosystem and community level of organization and on the maintenance of interactions between species as the key to study resilience. Okay, so if the key to study resilience is the species interactions, one way to look at species interactions is to represent the species through what we call an ecological network. And you have here a schematic representation of an ecological network where each Barents Sea, we actually have a relatively good idea of the species composition in the system. And as we've heard yesterday, I think this Carlos Duarte's talk that the Barents Sea is a relatively simple system, so we have good descriptions of it. And we have constructed a number of these networks. I'm showing here 4 examples of networks that have been constructed. These are fairly recent. There are a lot more that have been published. But you see here that these are simplified representation of a subset of the species in the system. What you can see also on these ones is these different studies, they have different focus, and they, for that reason, they have constructed different types of networks. For example, on the top left, a study which main focus was on fish, you can see that phytoplankton is represented as one single taxon in this network, whereas if you go to the bottom right, where the focus is on plankton, then of course there's a much greater diversity for phytoplankton. So what's important here is that we different questions will lead to different representations of the networks, and of course these different representations will yield different results. What is less perceived usually is that given a particular focus and given a particular set of species, there is not always a single way to draw the network, and small variations in representations are possible. What we know from network theory is that small variations in the network structure can sometimes lead to big changes in the network properties. So the sensitivity of our analysis of networks to the network design is something that we still have to work quite a lot on. So now, if we can draw networks from our basic knowledge of interactions between species, we need to analyze this network structure. And how can we do that to infer some information on resilience? We can do it through a number of information. One of them is diversity. You can look at the diversity of nodes in the system. How many species, how are their relative abundance distributed? We can look at redundancy. How many species perform the same role in the system? So you can see here at the bottom right, 3 species that have exactly the same trophic relationships in the system, so they are deemed redundant in the system. And we can also look at connectivity, that is how the different links are set up in the system. We've heard also yesterday that they can be hubs, that is species that concentrate many links, whereas there are external nodes that don't concentrate many links. There are configurations of the connections that make the system more robust or less. And there are parts of the system that can be heavily or not heavily connected. As you can see here, there's two main blocks that are fairly well separated in that representation, only linked by the top predator, the blue sector at the top. And it's by combining these indices of diversity, redundancy, and connectivity that we can actually achieve some quantitative analysis of resilience. This is even more exacerbated by amplification loops in the system. And of course, the direct consequence of increasing heat is also the melting of ice, which we also heard quite a lot about. But what ice melting does, it reduces the geographical coverage, it reduces the thickness of the ice, and by doing this, it actually increases light penetration in the water. So we will have two combined effects, the increase of heat and the increase of light to the system. So the total energy going into the system is going to increase. And it's not obvious how this will affect the communities at the lower end of the food web, in particular because of the balance between increase in photosynthetic rates and respiration rates that result from this increase in light and heat. So aside from energy input, the other kind of perturbations that we can expect is the occurrence of invasive species. Invasive species are usually characterized by the lack of predator. They have fast growth, population growth, and they usually they can rechannel quite a lot of energy in the system by predating on the number of species. This is quite a disruptive effect on the system, and we have good examples of invasive species in the Barents Sea. King crab and snow crabs are good examples of that. And here I'm showing you the example of king crab, which is well known to many of you, where we can see the distribution of king crab as it was in the mid-90s in dark red, and the distribution of king crab as it is today in pink, and you can see that the extent has increased by a factor of more than 3. The other thing that fishing does, which is quite important, is fishing is selective on size, so it will primarily remove large and old individuals. And what you can see on the bottom left graph here is the evolution of the mean size, the mean maximum length of fish in the global ocean and in the North Atlantic. And you see that globally, large fish tend to disappear from the system. This is even stronger in the North Atlantic. And of course, in the Barents Sea, the same phenomenon is occurring. And what you can see on the bottom right is the age distribution of cod in the Barents Sea as it was in the late 40s and early 50s, and as it was in the early 2000s. And you can see that in the late 40s, most of cod was age 9 and above, but in early 2000, most of the cod in the Barents Sea is age 9 and below. So it's so that's, I think, puts us in a good situation to study resilience. But we still miss some key elements to assemble the puzzle of resilience. And I'm just listing here some of these. I think when it comes to quantitative analysis of networks, we have drawn a lot of networks, mostly trophic networks, but there has been very little analysis, quantitative analysis of what is the structural properties of this network. Are they stable? Are they robust? And are they resilient to perturbation? The design of the network has been done very often in a relatively ad hoc way, and in most of the literature you will find a representation of the network that is like the best representations the authors can provide given the data they have, but they haven't investigated what is the sensitivity of the network designer to their result. I think here we have to be very careful in the way we design these networks and how they are sensitive to slight differences in design. Then spatial and seasonal decoupling. I've talked a little bit about this. I think we are now close to making some projections of what the future spatial or seasonality distribution of species may be. We have to investigate how that can influence the interactions between them. And finally, something I haven't talked very much about, but which I think is extremely important, is to really start working on scenario modeling. We have to do it. We have to provide some projections of what the future may be. And what I mean by this is not projecting the state of the system as it will be in the future, but to project the trajectories that can happen in the future. That is, project what the types of configurations that the system may have rather than its exact state in the future. And we as scientists are the ones who can do that, but we have to do it, and we have to do it well. That means that we also have to do it with careful account of all the uncertainties in what we put in our model, the uncertainties in our conceptual models, in our model design, in our numerical implementations, and we have to be able to communicate these uncertainties to the users of this model output, in particular the public and policymakers. So before I conclude, I'd like to thank again my co-authors on this presentation. And remind you that this is part of a project called BARECOR, the Barents Sea Ecosystem Resilience. And if you want to know more about this project, you will see a poster presentation that applies to the poster session this afternoon. Thank you very much.
Interannual variability in some of these key species or some of the primary species that are fisheries targeted or food for fisheries targeted species. Are you going to include some way of assessing whether certain highly variable parts of the population of the community are more or less resilient? Or is the community more or less resilient because of this inherent wide variability?
Yeah, the issue of variability and resilience, stability and resilience is a difficult one, but it's, again, we go back to the question of scale. And I will give you here an example of resilience and instability that comes from my past background, working on small pelagic fish in completely different systems. But if you look at small pelagic fish in the humble current, sardine and anchovy, you can draw a parallel between these two species and maybe herring and capelin in the Barents Sea. But the difference is that in the humble current, they have sediment records, and they can reconstruct the history of the two species for 2 millennia. And what we can see there is that in the recent decades, we've had huge shifts between sardine and anchovies. And these, you can call this shift tipping point or regime shifts. But if you look back over 2 millennia, these shifts they've occurred systematically for the last 2 millennia. So it's part of the dynamics of the system. These swings between sardine and anchovy, they are to be expected. It's not something unnatural or unexpected. It's something that is there in the dynamics of the system. For the Barents Sea, we have huge swings also. We have witnessed huge swings between herring and capelin, but we don't have this 2,000-year record to tell us whether this is the normal state of the system to shift from one to the other. So when it comes to variability, I don't have a definite answer to how we can include that in our analysis. But I think that we need to keep in mind that these things do happen, that they happen at maybe temporal scales of decades, of few decades. There are scales that we will witness during our career as scientists, that a manager will witness when they have to take decisions for managing the stocks. And we have to develop models that can account for that.